Welcome to the Picture Language Seminar. It's a great pleasure today to have Liang Jiang from the University of Chicago, the Department of Molecular Engineering. He got his undergraduate degree at Caltech and PhD in 2009 with Misha Lukin at Harvard. And today, Liang Jiang, who's a big expert on quantum information, is going to tell us about path-independent quantum gates. So this floor is yours. Please share your screen.
Okay, and does it work, Arthur? Can you see my screen now?
Works perfectly.
Okay, great. Yeah, well, first, I'd like to thank Arthur for giving me the opportunity to talk about some of my results about path-independent quantum gates. And this is a work in collaboration with many people, including both theorists and
Liang, something happened to the screen. It doesn't show.
Okay,
that's better.
Does it work better now? Yeah.
Yes.
Okay, yeah. Somehow when I switch on the laser point mode, it just does the characters kind of smeared out. Yeah. So this is actually a joint collaboration between theory and experiments. So I'll maybe first tell a bit about kind of the motivation and the theory, and then I'll talk about some of the experimental data which demonstrate the path-independent gates. So maybe let me start with kind of the motivation, why we actually want to study something called the path-independent gates. So this is related to the situation that we want to control a quantum system, which I call the central system, with an ancillary system. So our central system can have a really long coherence and well isolated from the rest of the world, but with limited control. So for example, you can think it as a superconducting cavity, which is essentially just a metal, you dig a hole in it, and the entire metal is superconducting. So the system can have a very long coherence time. So if it's a aluminum cavity, you can get easily tens of milliseconds, or if it's an niobium cavity, it can push even to seconds, really long coherence time. However, those systems you have a limited control. Maybe you can just coherently drive the system, or at most kind of do some squeezing. But those operations are limited because they are called Gaussian operation that you cannot do universal control. So all the states you can pair have a non-negative Wigner function. So, but we want to use the central system to store and even process quantum information. So in order to do that, we actually introduce something additional called the Ancilla System. So the Ancilla System, it actually can give us more control because it may have nonlinearity. So for example, we can have a Josephson devices in the Ancilla System, which can give us superconducting qubits, which here I call it a transmon, which is a particular design of superconducting qubits. So the Ancilla System with its nonlinearity can give us high control power. For example, it can give you universal control, give you all the gates and the readouts and the initialization. However, the Ancilla System also has a limited coherence. For example, the superconducting qubits, the coherence time is about like fractions of a millisecond, which is much shorter compared to the central system. Okay, so now the story is that we want to use the Ancilla System to help control the central system, which is a benefit gained from the Ancilla System. On the other hand, we actually don't want the noise of the Ancilla System to destroy the information stored in the central system. So that is the dilemma that we want to actually study. So the key question for this talk is actually, can we achieve ancilla-assisted quantum control? However, at the same time, not limited by the decoherence of the Ancilla System. So more specifically, can we achieve a universal control over the central system or do some logical operation over the central system, but not suffer from the decoherence of the Ancilla System? Okay, so here, it depends on the noise of the Ancilla System in the first place. If the Ancilla System suffer from static, kind of like a unknown frequency shift or some like a Hamiltonian drift, then actually we can use something called a dynamical decoupling to suppress it, like a spin echo, which in this case, it's actually relatively easy. But in practice, however, some of the ancilla noise, like a superconducting Josephson device decoherence, is actually more like a white noise. So it is much harder. And usually the traditional spin echo method, which is a quantum control with unitary operations, will not work. The simple argument is that the ancilla noise, like a dephasing or decay, sometimes it may, a depolarization, it may introduce entropy. And in that case, the unitary operation will not help us to extract the entropy and suppress the ancilla noise. So that method will not work for this situation. And moreover, generally you can say the gate-based error correction kind of like it actually has a limited application for such evolution situations. Because one may say, what if we do the full error correction scheme for it? And in this case, one actually need to be careful, because now in our case, the central system has more energy levels in there, and one should be carefully analyze the fault tolerance when the ancilla system has error. So the central system might go to a much larger Hilbert space, then one need to be very careful if we want to apply the fault tolerant formalism from the traditional error correction literature. So here, I would just maybe propose a method or propose a new criteria, which I'll call the path independent criteria, which will ensure that actually the ancilla noise with the measurement of the ancilla, you sort of can extract the entropy from the ancilla while at the same time still preserve the quantum information encoded in the central system. Okay, so here is actually the plan for the talk. I'll first give an introduction, review how actually we can use ancilla to assist the central system to achieve a universal control. And the example I'll give is called the selective number-dependent arbitrary phase gate, the SNAP gate. Then I'll point out when the ancilla noise comes in, this will be a challenge for such a system, for such a method. Then I'll give some example with an improved SNAP gate we call the path-independent SNAP gate that can overcome the ancilla noise and show even some experimental data. And finally, I'll give a general formalism about path-independent control schemes. So let me start with this special case for the SNAP gate. So let me just maybe be more specific about what is the central system, what is the ancilla. So in this case, here picture on the left, which shows a superconducting cavity. It's a piece of aluminum which have these two holes. Each of the hole corresponds to a cavity mode. And one will cause the storage cavity, and the lower one will be the readout. And these two cavities are connected by a semi-transparent chip, which hosts a Josephson device, which we call it a transmon superconducting qubits. So basically, the focus of the talk will be actually related to the storage cavity and a transmon device, which is a Josephson nonlinear device. So in case people are less familiar with it, you can think it as a transmon device as an aharmonic oscillator, which is kind of generated by the cosine potential of the Josephson energy. And because it's close to the bottom, it will be close to harmonic. So you can think it more like an oscillator at close when you have lower excitations. But when you go higher excitation, you start to see the aharmonicity of the trapping potential. So therefore, the energy level spacing will be different. And it is this difference of the energy level spacing that enable us to selectively drive the lowest two energy levels, which sometimes we call it a transmon qubit. So that gives you, it's a nonlinearity of the Josephson energy that gives you the effective two-level system as a superconducting qubit. And here, usually people will just use the lowest levels, which called the ground and the excited states. And in the later part of the talk, actually, I will also need a second excited level. I call it the F level. Okay, so now let's just tentatively assume the transmon, the Josephson device is just a two-level system, and the storage cavity is just a harmonic oscillator. So this is effective Hamiltonian of the harmonic oscillator, which is our central system, and the transmon device, which is our effectively ancilla system, which help give us the nonlinearity for the control. And when the cavity and the device and the transmon, they have different frequency, then essentially there is no physical exchange of excitation between the two. So there's only virtual exchange of excitation between the two. And when you go to this higher order perturbation, you will find that it's effectively a dispersive coupling between the cavity and the ancilla system. So basically what you get is that this dispersive coupling, which you can interpret as whether the transmon is in the ground or excited state, it will shift the frequency of the central system cavity. Or you can think the other way is the number of excitations in the central system will shift the energy level, especially the energy of the excited level of the transmon. Okay, and this energy shift is of order scale of order megahertz, which is actually 2 or 3 orders of magnitude than the decoherence of the system and ancilla. So therefore, you can treat it as with a short time evolution, you can just treat the whole system and ancilla evolve under this effective Hamiltonian. Now, again, just to remind us that actually our cavity is really long-lived with millisecond or even longer tens of millisecond coherence time, while this ancilla is short-lived with only like 100 microsecond coherence time, which is a fraction of a millisecond. However, we can actually, in addition to that, with the recent advances of superconducting kind of technology, people find out ways to do like a quantum non-demolition readout of this ancilla with high fidelity and in a short amount of time. And moreover, with the FPGA adaptive control, you can even do a real-time feedback. Okay, which is actually important if you want to do full quantum error correction. But here for this talk, it's actually what's more important is that you have a capability to do the non-demolition readout of the transmon. Here, non-demolition means when you read out this transmon, you do not destroy the state stored in the cavity. Okay, so now with this effective Hamiltonian, which is the dispersive coupling between essentially a 2-level system and a harmonic oscillator, we can actually explore what's the possibilities of control. So there are 2 control knobs we can have. One is we can drive the cavity system by resonantly applying a microwave field, which is at the same frequency of the superconducting cavity. Or we can selectively drive the 2-level systems of the transmon by applying different frequency tones. So here, actually, I'm writing down this different frequency tone as an omega transmon minus integer multiple of the frequency shift depending on different photon number of the cavity. So this is actually, you can just control different tones or do the pulse shaping to enable the driving of the transmon with different frequency tones. Okay, so now it's probably like easier to visualize what is the energy levels and the drives. So let's tentatively go to the rotating frame of the cavity and not driving the cavity, just driving the transmon. So in this case, here as the energy levels, the 0, n equal to 0, n equal to 1, 2, 3, just label the number of excitations in the cavity. And the ground and excited states correspond to the state of the transmon. It can be the ground manifold with different cavity photon numbers or the excited manifold with different photon numbers. Depending on the photon number, actually the energy level of excited state is shifted by integer multiple of chi. Okay, and since the system has high coherence, we can selectively drive the transmon conditioned on different photon number. For example, in this case, I say conditioned on there are 2 photons, you can drive the transmon from the ground to the excited states and even drive it back. So here is one possibility. You can drive it from ground to the excited states and then drive it back. But the 2 pi pulses that you apply to the drive will have a relative phase. And that can enclose an area on the Bloch sphere associated with these 2 levels. And this will accumulate a geometric phase for the photon number 2 state in the cavity. And that is what we call kind of like a selective number-dependent phase gate. Okay, but for the other photon numbers, because the drive is very selective, it's off-resonant, so essentially there is no phase accumulated for other photon numbers. So for this particular pulse, you can accumulate a phase for the n equal to 2 photon number state. And the magnitude of the phase accumulation is proportional to the area that's enclosed. So now, we can also simultaneously apply these different drive with different pulses. And then that will allow us to simultaneously accumulate different phases for different photon number. And we call this the selective number-dependent arbitrary phase gate. And if we write in terms of a unitary, then that will actually allow us to map an arbitrary superposition of a state which has a photon number n, coefficient Cn, to a new state, which the Cn will be multiplied by a phase factor e to the I phi n. And in terms of writing a unitary, this is essentially saying that I will apply a phase e to the I phi n to a photon number n. And the phi n is of our choice, which is controlled by applying a different relative phase of these pi pulses for different frequency tones. So therefore, we can choose arbitrary phi n. So when phi n is a square with n, then essentially we have a Kerr effect. When phi n is proportional to the powers of higher powers of n, it will be higher order of Kerr effect. So that gives us the nonlinearity over the harmonic oscillator, which is actually effectively borrowed by the nonlinearity of the two-level system. So this is what we call the selective number-dependent arbitrary phase gate, snap gate. However, the snap gate by itself is not universal. As you see in this level diagram, it doesn't change the photon number. So in order to complete the set of universal control gates, we need to drive the cavity, which corresponds to a displacement operation for the harmonic oscillator. And when we do that, basically you can see that all the energy levels are connected, and with a bit more careful analysis as detailed in this paper, you can show that you actually have a universal control of a cavity transmon system with just driving the cavity and driving the transmon. So that is actually kind of like the background about the universal control of these operations. So just to give you an idea about like how we can use this universal control, since we have cavity drive or the transmon drive, which give us a snap gate, you can just alternate in the two drives. So suppose you start from vacuum, you can just displace the cavity, apply a snap gate, and then displace the cavity back. And that simple sequence can allow you to prepare a single photon on demand. So here's a kind of a diagram and some experimental data just illustrate how this can be done. So this is a Wigner function diagram that you see, and you see that displaced kind of like a distribution, which corresponds to a coherent state, which is displaced from a vacuum. And here is a photon number distribution. And now, once you dial the phase of the photon number 0 state by applying extra pi phase shift for that particular level, you'll find the Wigner function suddenly have a negativity in the middle. And then then you can actually perform a displacement back to the origin. Then what happened is that in the photon number basis, there is a constructive and destructive interference, which will essentially eliminate the population at different photon number, except population in photon number 1, which has a constructive interference. And in the Wigner function plot, you actually see the 1 photon Fock states. So this actually shows that experimentally, these are the experimental data in the middle row, that we can prepare a single photon on demand. But this is for state preparation. We can even do something more. And we can even prepare some like universal operations over higher photon numbers. And since the operation gets more and more complicated, we may relax the requirement of separately driving the cavity and the qubit. So here is a sequence of the cavity transmon drive and the cavity drive. So the solid and dashed line correspond to the real imaginary part associated with the drive. So now you will find that actually applying a sequence of order time 1 over chi, which chi is about over the megahertz, 1 over chi is over the microsecond. So that allows us to achieve some quantum gates. And here is just the one particular coding for the CAD code. We can actually perform a quantum gates. And this time of 1 microsecond, which is much shorter compared to the transmon coherence time, but still it may introduce error. So if you do a gate over a microsecond, while the coherence time is over like 100 microsecond, then you will actually, there's a 1% chance that during this operation, the transmon may relax or dephase. And that may introduce about the percentage level error. So here is actually a randomized benchmarking, which basically just repeats the gates many times. And as a number of the repetitions, you'll find that the performance, the gate fidelity decreases. And you will, from this extrapolation, you'll find that actually the gate may have all the percentage level gate error. Okay, so with the error probability of order percentage, which is consistent with the gate time and the transmon induced decoherence, that is actually poses a challenge. Okay, that currently these snap gates are limited by the decoherence of your ancilla. So you want to control your central oscillator system, but your ancilla transmon or Josephson device pose a limitation about the coherence or the quality of the gates. Okay, so now this is actually the challenge, that can we achieve the ancilla system quantum control not limited by the ancilla decoherence? Okay, so I hope that the question is clear. And now maybe let me just try to give a more intuitive picture of how to overcome this challenge. So actually the intuitive picture we have in mind is actually very similar to our kind of like undergrad mechanics, which is something called kind of path-independent line integration. So if you remember, like in kind of classical mechanics, there is something called like curve-free vector field. When you do integration from one location of the work to the other, you'll find that actually it doesn't depend on which path it goes. It will always be the same amount of work that you done, and which is associated with kind of like the potential difference between those 2 points. And here, it's actually also something similar. But instead of the kind of the path in the physical space, we may have a path kind of in the path integral. And what we want is actually kind of the path in the path integral for the open quantum system to give you the same unitary evolution. Then essentially, it doesn't matter what the system is going on, you will always get to the desired unitary evolution, which is what we call the path-independent gates. So here is kind of like a just reminder, we're a central system and ancilla system, which are coupled. And you can think that your central system has the initial quantum information stored, and you want to use the ancilla system to assist the control of the central system, so that at the end, you will apply a unitary operation over your central system. But as I said earlier, the ancilla system introduced noise, which may increase entropy. So to extract entropy, what you do is actually measure the ancilla system, which will tell you information about what happened over the central ancilla system. And that will extract entropy. And the condition on the measurement outcome is sort of know what the unitary is applied to the central system. So the unitary applied to the central system, depending on both the initial state and the final state of the ancilla, which can be measured. Okay, but generally there is no guarantee it will be a unitary operation. But for the path-independent conditions, then this sort of is a condition we want to achieve, so that it will be a unitary, only depending on the final state of this ancilla system. So you can think that kind of in the path integral, that you start from the ancilla system with some initial state I at time t0, and then you evolve, it will, after the measurement, it will end up in the state F at time t final. And there will be different paths going on during the evolution when you do the control. We don't know which path it takes, but as long as the different paths give you the same unitary evolution, then you actually achieve a unitary control over your central system, and which ensures that the information encoded in the central system is not destroyed. So unitary may or may not be the desired unitary, but it's okay. As long as you know it is a unitary operation, then you can repeat this procedure until you achieve the desired unitary. So this is kind of the key picture about the path-independent control. Now, let me maybe go through like one example of how to do path-independent snap gate using superconducting circuits. So here is actually like maybe a bit crowded slide, but let me start from the upper right panel. Again, we have the transmon with the lowest 2 energy levels denoted as excited and the ground state. And the system actually may have decoherence. The excited state may relax to the ground state due to excitation loss. And that's kind of one of the major challenge. And in addition, the excited states may have kind of like energy level shift due to some environmental noise, and that will cause a dephasing for the excited state. Both relaxation and dephasing are important for these practical systems. So here in the master equation notation, I have this kappa GE correspond to relaxation from the excited to the ground state. And the gamma GE correspond to the relative dephasing between the ground and excited levels. And here, this part is correspond to the dispersive coupling Hamiltonian and the driving that we can apply to drive the cavity or drive the transmon. Okay, so, but the key point is, during the evolution, if any of the relaxation or dephasing happen, it will interrupt the evolution, and generally it will cause a decoherence or information loss in the cavity system. So now, to overcome this, the key idea we want to do is to introduce a redundancy in our ancilla system. So instead of a two-level ancilla, we actually use the third level of the transmount, which you can think it as an aharmonic oscillator. So it's okay, you do have a third level available, and also selectively addressable by using different driving tones. So instead of using the ground and the excited level, we actually use the ground and the second excited level, we call the F level, to control and performing quantum gates. So you see, like, immediately there is a benefit, because if you use the ground and the second excited level, if there is an excitation loss, it will, the system, the transmount will be projected to the first excited level, which is distinct from the initial state you start from. So this will immediately allow you to detect whether or not there is an excitation loss. So whenever there's a single excitation loss, you will be able to detect such an error. Okay, and here I should clarify that due to selection rules, there is no decay from the second excited level to the ground level, which it actually holds very well for transmount systems. So the decay kind of only go like one by one. Therefore, you can detect the decay. Moreover, you can also engineer the coupling between the system and the ancilla, so that the second and the first excited levels, they have the same amount of frequency shift over the cavity. So therefore, for the cavity, it doesn't matter whether the transmount is in the second or first excited level, it will have an equal amount of frequency shift. And this can be experimentally achieved with some additional controls. So once we have this, then these are the two conditions that will enable us to achieve path-independent control of a selective number-dependent arbitrary phase gate. Okay, so now let's maybe instead of going through, before going through the procedure of analysis, here is actually the result. So after these path-independent control, we'll get, if we end up in, we'll measure the transmount at the end. It will give you second excited state, first excited state, or the ground state. If it ends in any of the excited states, it will give you the snap gates that you want to achieve, mission achieve. If it's in the ground state, then it will just give you identity operation. So you just need to repeat the experiment again. So that was actually what's the nice kind of like a property of path-independent gates, that it tells you whether or not it's successful. If not successful, the information is still complete and you can repeat the operation until you succeed. So now let's maybe first have a simplification of what I mean by snap gate. Because earlier, the snap gate I talked, you need to do 2 pi pulses to carve out an area in the Bloch sphere to do the quantum gates. But actually, you can do it much simpler. You actually just need to do 1 pi pulse, and that's already sufficient to do the gate. So here is the scheme. So you start, suppose, from a superposition of 0 and 1 photon number states. Of course, you can have more, but here, just for simplicity, I only consider these 2 terms. And the transmount is in the ground state. And related to our discussion, we will use the second excited state of the transmount that allows you to drive to control this cavity system. So in order to control these, we'll need kind of like 2 different drive tones from G to F. One is at the kind of like you can have effective Rabi between them, and the other drive tone, which is slightly shifted by frequency pi. Okay. So with these 2 different drive tones, and the Rabi oscillation amplitude is much stronger than the dispersive shift chi, then basically you will selectively, the first frequency drive tones will only drive the transition between G0 and F0, because that's what it's resonant to. And the second drive tones will drive the transition between G1 and F1, which is the second drive tone. And the reason I want to separate these 2 is because the first drive tones will only drive the G0, F0 transition with the phase phi 0, while the second drive tone will only impart the phase phi 1 to the G1, F1, that transition. Okay, so after that drive, for time pi over omega, 2 pi over omega, pi over 2 omega, then essentially it did a pi over 2 pulse, go from the ground states all the way to the excited states for both cases with 0 photon or 1 photon. However, they will accumulate a different phase depending on 0 or 1 photon, because they are driven by a different drive tones with different phase. And here I'm already transitioned to the rotating frame associated with these two different transitions. But notice that there are different phases, which is exactly gives us the snap gate. And notice that in this framework, in this description, I do not need to drive even the second tone. But in principle, you can if you want to drive like a kind of a very strong pi pulse with the same phase, then you actually can drive it back and enclose different areas proportional to the phase angle phi. But here, for simplicity, I'll only need to drive a pi pulse. That's already enough to do the snap gate. Okay, so I can imprint different phases for different photon numbers. Now, let's see, like, what if I have dephasing of the ancilla during this process? So suppose when I do the drive, and halfway of the evolution, and because I'm driving both of these, so both 0 and 1, they will have the rotation angle which rotates between the G and F. But I'm still at the halfway of the evolution, so the theta angle haven't goes to pi yet. Okay, but haven't goes. So basically, I still need to wait until the gate to finish. However, during this time, there is a dephasing happen. So dephasing can be described as a quantum jump operator, which kind of like shifts the F level by a pi phase relative to the ground level. And when this happens on the Bloch sphere, it basically goes to the opposite side of the point on the Bloch sphere. However, even though it goes to the opposite side, it still goes on this, stay on this big circle, which is specified by this phase angle phi1 if there's 1 photon. If there's 0 photon, it's still on this big circle, which is specified by this phase angle phi0. So mathematically, you can write down this expression, and then the system will evolve for the second half of the evolution to at the end of the time pi over t over 2. So at the end of the evolution, you will find that actually you will end up in a superposition of G and F, and also 0 and 1. But if you look at the terms associated with the G0 and the G1, actually they have the same coefficient, which is associated with the probability amplitude it's in G. And the terms with F0 and F1, they will have the same magnitude, but will have a different phase which associated with the drive that you imparted. Okay, so now if you actually projectively measure the ancilla in G or F, if it's in G, then essentially nothing happened. You end up in the same state you start with. If it's in F, you actually accumulate a phase phi0 and phi1. Okay, so now that will actually give you a snap gate if it's end up in F, and it will give you identity operation if it's in G. So basically, we reach a conclusion that the path independent gate is actually first order transmount dephasing error. It can actually like immune, because it will either give you a snap gate or it give you identity operation, and you can repeat until succeed, you get the transmount, you get the snap gate. And moreover, actually, if you look at more carefully, the whole scheme actually can allow you to suppress arbitrary order transmount dephasing error. It's because it can go back and forth many times as long as it stays on this same big circle specified by the angle phi n, where n is the photon. So therefore, in the end, you actually can get like always the same conclusion. If it's in F, you do the snap gate. If it's in G, you do the identity operation, regardless of how many dephasing errors happen during the process. So it can be path independent for arbitrary order transmount dephasing. Okay, so here is kind of like another way to visualize it, is we go back and forth between G and F. When you go from G to F, you will implement a snap gate with a sequence of phases, theta. And if you, from F to G, it actually will give you a snap gate with phases of negative theta. So whenever you go a loop, you will actually have 0 phase accumulation. Okay, so basically that is kind of the unitary that associated with any evolution time alpha, which is proportional to the duration of the drive. And you'll find that either there is a part which is proportional to identity, or there's a part when you go from G to F, there will be a phase imprinted, or if from F to G, there will be a negative phase imprinted. So you can now think in terms of time trajectory. Whenever you kind of oscillate back from G and F, whenever you go to F, you will imprint a phase. Whenever it stays in G, it did nothing. You can even go back and forth between G and F many times, but what matters is, in the end, where it's ended in. If it's ending F, you imprint a phase. If it's in G, we did identity operation. So this works for arbitrary order for dephasing error. And that's really good. It's indicating that we have a path-independent snap gate for arbitrary order ancilla dephasing error. So now, so far I only talked about the dephasing error, which seems to be an easy one. What about the relaxation error? And as I mentioned in the error model, when you have relaxation, so the second excited state F will be relaxed to the first excited state E. Okay, now, and actually we impose a condition that E and F will introduce the same amount of frequency shift for the cavity. So that actually enables us to achieve something called the kind of a noise, kind of like transparent kind of subspace. And so what happened is the following. So suppose there is a relaxation error happening in the middle. The relaxation must come from F to E. So somewhere earlier, go from G to F. And when it goes to F, it will accumulate this snap unitary S theta. And then the relaxation happens. And then actually after that, it will, the claim is that, okay, at E level, it will accumulate the same relaxation unitary, which is inherited from this F level. Okay, now the question is, we don't know, we only know relaxation happened during the duration from 0 to time t, but we don't know when the relaxation happened. And it turns out this is completely okay, is because the underlying Hamiltonian, the E and the F will introduce the same amount of frequency shift to the cavity. So therefore, actually it doesn't matter how long this duration is, it actually will introduce a trivial evolution, and all the evolution doesn't depend on when this relaxation happened. It will always give you the same output unitary. Or you can think it as there's a relaxation operation, go from F to E. It actually commutes with the underlying Hamiltonian. And so that actually you can, even the relaxation happened in the middle of the evolution, it is equivalently as if the relaxation happened at the end of the evolution, which is what we call the error transparency condition, which was first proposed by Elliott Qubit in 2018. So with this error transparency condition, we actually get, you can treat this F level and E level as if they're the same level. It doesn't matter whether how many times they go back and forth, they will give you the same evolution as the snap operation S theta. So basically, whenever you have this shaded kind of region of this noiseless ancilla subspace, essentially you can just treat it as kind of a degenerate levels, which has a trivial evolution associated with the dynamics on the ancilla. Okay, so this actually only works for the first order of relaxation error, because I can only take one hit from F to E. But if there is another operation from decay from E to G, then I'm screwed, because I don't know whether it's originally from G or it is coming from another path from F to E to G. And that's why actually this only suppresses the first order relaxation error. And if you want to suppress high order relaxation error, you can actually push it to higher excited levels, F, H, I, or high excited levels of the transmon, then it will take higher order relaxation. But in practice, this probably will be a bit challenging experimentally, because you need to have more controls and need to do the chi matching for higher levels as well. Yeah. So now, this is for relaxation error, and earlier we talked about dephasing error. So when we put these together, it basically says that with all these different passes, as long as there is only at most one relaxation, and with arbitrary number of dephasing, you will satisfy this path independent condition. So all these different passes, which can go from G to F, you will implement the snap operation. Or the paths go from G to E, you also implement the snap operation, and also heralding there's a relaxation error. And if it ends up in G, it will give you the unitary operation, which is actually identity. So you need to repeat the operation. Okay. Yeah. So in terms of the magnitude of the error analysis, so basically we'll have three possibilities, F, E, G. And the probability end up in F is of order 1, and in E is of order kind of 1 over T1, which is the relaxation time. And it's end up in G, it's 1 over T5, which is the dephasing time. And you can also estimate the infidelity. When you multiply the probability and the infidelity and add up, it will give you the average infidelity. You will find that average infidelity is always at the second or third order of the relaxation or dephasing error. Okay, so therefore, basically, you will be able to suppress the error to higher order compared to the conventional method, which the error is only always the first order of relaxation or dephasing. Okay, so that's basically kind of like the summary of kind of the protocol. Now we can also kind of like actually also ask our experimental colleagues to help to demonstrate this idea. And so basically there's a G, E, F associated with the ground and the first and second excited level of transmar. As I said, actually G and F, we cannot directly drive them. So you need a 2 photon tones, 2 photon transitions to drive the GF transition. And once you did it, you can also selectively drive depending on different photon number in the system. So the initial state of the system, you can kind of like prepare some particular states, which is some superposition of 0, 2, and 4 photons. And if it end up in the F, E and F, you will find that actually you will have the desired, a different shape of Wigner function from the initial state. And that's actually exactly consistent with the simulation that it will end up in this Wigner function, which has a kind of like a red in the middle, blue on the side. And this actually corresponds to actually a different logical states with this binomial code. But in the G, it corresponds to the initial logical state of the binomial code. And you will see that there is either no operations or the successful quantum operations being applied if it's end up in E and F. Okay, so practically, we actually do want to completely achieve the operation. So if it's in G, we may want to repeat the operation until succeed. So that's kind of the logic, is that we try to do this operation and we measure the ancilla. If the ancilla is in G, we actually need to repeat the procedure. If ancilla is in F or E, we basically just need to adjust the phase and finally give the output. So experimentally, you can use FPGA kind of to do this real-time adaptive control. And here is actually the experimental data. So these are just look at the lower right panel with these 2 different curves. The blue is correspond to the operation without this ancilla monitoring, and the red correspond to the ones with ancilla monitoring, which the slower decay indicating the gate has lower error. And from these decay curves, you can extract the gate fidelity without ancilla kind of this monitoring, the passing dependent gate, it will be of order 5%, while with kind of the monitoring, it actually reduced at least by a factor of 2. Yeah, so that indicating actually the system is working, but of course that this number is not like really suppressed to the second order. It's partly because there are also other imperfections associated with the measurement or associated with kind of the kind of tuning the Hamiltonian. The system might leak to higher excited levels. So all these are the things that will be further improved in the future demonstration, but at least there is an improvement in it. And we can also further verify that we're indeed suppressing the relaxation, ancilla relaxation error. So we're indeed like the system, central system is immune to the ancilla relaxation. So here is, there's a way to first enhance ancilla relaxation by kind of like driving, kind of induce, stimulates the decay from F to E. So here, the black dashed line indicating that the population of E will increase if we increase ancilla relaxation rate. And which will kind of like be an approach to kind of increase this additional detrimental noise for the ancilla. But on the experimental side, this is before the passing dependent gates. But when we apply the passing dependent gates, the logical error will still remain very insensitive to this enhanced ancilla relaxation error. And on the right panels, it corresponds to enhance the dephasing error, while experimentally, we will see that if we do regular operations, the error will increase, but if we do this passing dependent control operations, actually the ancilla errors will actually be less sensitive to this injected dephasing error on the ancilla. Okay, so basically it just illustrates that indeed the whole system is more robust against the ancilla errors while we performing these operations. So maybe so far I'm mostly focusing about the special case in the superconducting cavity systems, but actually there's a way to further generalize the formalism. So the general setting is actually, we can look in this diagram with the central system on the ancilla. And we just want the ancilla, whenever it ends up in the final state, all these unitaries, all these evolution trajectories will give you essentially the same unitary up to an overall phase. And now we can consider there's the D-level ancilla, which may have ancilla relaxation or ancilla dephasing. And in practice, maybe the central system may also have decoherence, but tentatively, let's pretend that the central system has much longer coherence. So let's not worry about the central system in the moment, but just focusing on the ancilla error. Okay, so now the question is, what is the general criterion that we can achieve a path-independent gate when there is such generic ancilla relaxation or ancilla dephasing errors? And here is actually the answer. It basically, we need to have kind of an isometry between, or they need to have an isomorphism between what are the operators that are relevant for the ancilla system and also what are the operators for the central and the ancilla systems. So let's maybe first look at the ancilla system operators. So these are the bases for the ancilla jumps from different like n level to n level. And these jump operators will satisfy this kind of like a operation. You go from D to C, and if another jump from B to A happen, you need to make sure B and C are the same so that this will give you the kind of the multiplication rules of the jumps. And for the Hamiltonian, the ancilla may also, you drive the ancilla, so your ancilla will need to construct the Hamiltonian. And the ancilla will have propagators from the Hamiltonian evolution and also jump operations. So that will ancilla, also this product of these operators should satisfy the rule. Basically, all the intermediate steps should have the same ket and bra to cancel, and you start from the initial state to end up in the final state. So these are in some sense the trivial algebra, kind of matrix algebra for the ancilla. Now for the central system, what you need, for the joint ancilla central system, you need to have kind of like a corresponding like isomorphism in terms of the matrix algebra you have. And in this case, you will notice that the first part of the operator is ancilla, and the second part of the operator is actually your central system. So notice that you cannot write any operators or any kind of matrix forms for the central and ancilla system. They need to kind of be able to be spanned by this basis sets of operators. And with the property that UMN, when you multiply kind of UAB, UCD, it needs to be equal to UAD. So they need to kind of like satisfy this set of rule, which associate with the jump operator. And similarly, the Hamiltonian should also pick or be constructed from this set of basis operators. So if your jump and the Hamiltonian, they all satisfy these sets of rules for your joint central and ancilla system, then there's a guarantee that your propagator and also will also satisfy those path-independent conditions. So the early example, when we look into this path-independent kind of like against the robust against dephasing errors, you will find that actually this UMN is basically either the snap gate e to the I theta, or it will be e to the minus I theta when you change the order of MN. So therefore, it does satisfy kind of this condition with the jumps and also the Hamiltonian. So therefore, that actually satisfies this general isomorphism between the matrix algebra for the ancilla and also the extended matrix algebra for the ancilla and the central system. So as long as this condition is satisfied, then actually you will guarantee to satisfy the path-independent formalism. So maybe just a short line of a sketch of the proof is basically there's a way you can generate these propagators from T1 to T2, which is consists of these jumps. But if it satisfies kind of this isomorphism, you will find that for the 0 jump, 1 jump, or n jumps, they will always be proportional to the same unitary that only depending on the subindex associated with the initial and the final state of the ancilla. So this is actually like a kind of the, so far, the most general formalism we have for the path independent condition. And once you satisfy it, you can have your ancilla start from initial state in the final state with different paths. And here, the open circle indicating there is some dephasing error happen. Then actually, if you satisfy the path independent conditions, you will guarantee these different paths will give you the same unitary. And if there is a noiseless ancilla subspace, then basically you can even have jumps within that noiseless ancilla space. The jump can occur at different times. It will still give you the same unitary. And you can also have hybrid of dephasing and jump. It will also give you the same unitary. So basically, you can have like a kind of like a combinations of relaxation and dephasing. It will give you the same path independent conditions up to the order of relaxation that you can tolerate. Okay. In principle, dephasing can be arbitrary order, but relaxation only always finite order, because in the end, everything will be relaxed to the ground state, then you will lose the control of the system. So just as a summary, basically I talk about introduce the formalism of general path independence using the ancilla. And by measuring the ancilla, you can extract the entropy from the ancilla noise so that it opens up the possibility that you may be able to perform unitary operation over the central system, even though the ancilla is noisy. Okay, and then we actually like show some experimental progress of doing this adaptive control with the path independent, and show that indeed the gate performance can be improved. And finally, give a general isomorphism between the ancilla system and the joint ancilla central system, which gives us the sufficient condition to achieve the path independent criteria. Yeah, so maybe lastly, let me just also comment that this path independent or this ancilla measurements is actually has a connection to the, in case people work on quantum error correction with the flag qubit, it does have a connection to that flag qubit formalism. But here it's probably even more hardware efficient because you just need the third level of ancilla rather than extra number of qubits, which will significantly increase the Hilbert space dimension. Yeah, and also like in principle, there could be also noise in the central system. And then in that case, we may also consider using some quantum error correction in the central system so that the error correction can also suppress errors from the central system, as well as maybe there's some imperfection of this operation. Then that error correction can also suppress errors from the residual non-perfectly canceled ancilla noise. So with that, I would like to thank all the theory and the experimental collaborators on this project. Thank you for your attention.
Well, thanks to you very much for a beautiful overview of this path independence. I'm sure this will initiate some discussion. So for the moment, why don't I end your screen sharing and ask if there are comments or questions or other things that we would like to know more about. John, you have your hand up. John Tyson, turn on your audio.
No, that wasn't a hand up. That was just a thumbs up.
Oh, thank you. Does somebody have a question? So maybe I could start by asking, what is the connection to flag qubit error correction?
Yes, so the flag qubit error correction is actually a formalism that people introduced about 10 years ago, which is try to also make it hardware efficient when you do error correction, because the standard error correction scheme, you need like many ancilla qubits, preparing even some like GHD states to measure. But the flag error correction is saying that you just need 2 extra ancilla qubits. You can perform error correction for like some of the 713 code or other smaller quantum error correcting codes, so that experimentalists, they can work on it without introducing too many qubits. And here, in some sense, it's similar because they want to reduce the number of ancilla qubits to do error correction. And here is that we kind of like want to minimize the extra resource needed. So we just use a 3-level ancilla to kind of like help us to give us extra information about what kind of error might happen, so that error correction can focusing on distinguishing those errors which are very likely to happen. So, and the flag qubit, you can think from the name, a flag indicating whether or not there's a flag, which gives you information what kind of error you need to focusing on to correct. So that's where the connection is. And I think both has a similarity that we can be more hardware efficient in terms of doing error correction, so that you can reduce the requirement of ancilla to maybe just a few level ancilla, or maybe just a small number of ancilla qubits. Yeah.
So is your method more oriented toward a particular implementation of qubits, or does it work across different platforms?
Yes. So this is actually exactly what we're trying to further generalize right now, because indeed, our original motivation is we want to make this cavity and the transmon system to work. And we actually say, oh, well, actually the transmon system does have extra levels, let's just use it, which turns out to be kind of like very helpful. And but I think that generally, maybe not every system will have extra levels, right? If you use some like a spin degree of freedom and so on, maybe you need to have an extra spin, which for those cases, like in the trapped ion platforms, maybe the flag qubit is a better fitting for that. But I think that theoretically, I think there is a common theme in there, which is actually to introduce a little bit redundancy of your ancilla. And if you know what's the error model for the ancilla, then you can actually very efficiently design this redundancy so that you can perform and kind of like use the ancilla to help to control the system or extract a syndrome from the system without significantly destroy the coherence of the system.
So does somebody else have a question?
Yeah, this is Rad. I have a question. So it appears as if that you're creating a topological phase on the transmon to control the cavity. Is that correct? Because it stays on the big circle of the...
Yes. So here the phase, sometimes we call it a geometrical phase, because it kind of carve out the area. Yeah. And it may make a different shape, but the area, it is the area that matters. Yeah.
Okay. So yeah, so I can see the advantage. You have a less number of ancillas to control the error. Typically, you use the error correcting codes to implement topological codes, but it's as if you're going in the opposite direction. Is that the correct way to understand?
Yeah, so here probably I would call it more like a geometrical rather than topological, because it can take a continuous values rather than kind of like with the wrapping number 0 or 1 or 2. Yeah, and but the whole scheme you may consider also have another topological kind of like surface code correction at the next higher level. That's also possible. Yeah.
So are there other questions or comments?
Can I ask a follow-up question?
Yes.
I just maybe just think, can this phase be used to other cases that can manifest the topological structure of the underlying like space of those path evolution of the gates?
Yeah, well, I think that's a good question. I haven't think that much because, but yeah, and so could you maybe further clarify what do you mean by the topological structure of the different paths in there?
Yeah, just like the wrapping or what you said, like wrapping or winding for 0, 1, or 2 or whatever.
Yeah, so I think that right now we're only doing this mostly driving the 2-level ancilla, right? And or even if we use a 3rd level, it's mostly for a dump, that in case something bad happens, it goes there. But I think it will be interesting if probably we can consider more sophisticated drive with the D-level ancilla, and maybe you can have even more sophisticated paths that probably can give you something, maybe, maybe something even beyond just an area. Maybe it can be something even more non-trivial to give you some operation. Yeah.
What causes the nonlinearity in the Hamiltonian that creates the energy shifts?
Yes. So the nonlinearity comes from the fact that we have a two-level ancilla system. And when you have a two-level system, the first nonlinearity you have is you have a saturation, right? And when you kind of drive the system harder and harder, it actually, instead of keep saturating, it will actually keep increasing the population in the excited state. It actually will go through Rabi oscillation. And that is the kind of the nature of the nonlinear two-level system. The nonlinearity gives you the saturation. And it's because of this nonlinearity, it allows you to do this Rabi oscillation or Rabi drive that accumulates an area in the Bloch sphere. And this is very distinct from a simple harmonic oscillator. Yeah. So we basically just borrow the nonlinearity from a two-level system, and by driving it, it actually gives us nonlinearity in the harmonic oscillator.
So it's more
Sorry.
red. Why don't you go on?
This junction has to be plasmon, or you could consider other superconducting systems as well.
Yeah, so far, like we're considering the transmon, but there are also other designs of Josephson device, like a Fluxonian or other different types of kind of Josephson device. And I think that this method could apply to those ones as well. Yeah.
Well, if there are no further questions, I want to thank you again for a really interesting talk. And you seem to be quite active in pushing this direction forward. So good luck in the near future. And we'll look forward to seeing your new results. Thank you. Thank you.
Thank you, everyone.
Bye-bye. See you next week.
Bye-bye.